In this video, we will complete the entire curve sketching algorithm for a polynomial function and a rational function. So we're going to be combining our knowledge from advanced functions when we graphed by thinking about the domain, about the intercepts, about any discontinuities. And then we're going to add on our knowledge of the first derivative, giving us the critical points and locating the local max and mins. And then going to our second derivative to find the points of inflection to determine the concavity at certain intervals of the function. And then we can put it all together in a sketch. So we're going to start with the polynomial function. And I'm just going to write it down before I scroll. All right, so the first part is going to be focusing on the advanced function side. So we notice that this is a cubic function with a positive leading coefficient, which means we will be going from quadrant 3 to quadrant 1. Now for all polynomials, the domain is from negative infinity to infinity, so we don't have to worry about any discontinuities. There's no restriction, none of that. I am going to find my y-intercept, so setting x equal to 0, and we get -1, so 0, -1. And now I'm going to find my x-intercepts by setting my function equal to 0, and then factoring. Now, to factor this, it is cubic, so I am going to do synthetic or long division. So first I'm going to try to find a factor of this function. I could use any factor of my constant, so plus or minus 1, and any factor of the constant divided by factors of the first coefficient, the leading coefficient. So plus or minus a third would also work. So when I try subbing in -1, I do get 0, which means x plus 1 is a factor. And to get the leftover, I'm going to do synthetic division. That's my personal preference, but you can, of course, do long division. So if I'm factoring out x plus 1, I'm going to write -1 out front. I'm going to write all of my coefficients and bring the first one down. Now, -1 times 3 is -3, and then add the column. -1 times 4, -4, add the column. -1 times -1, +1, add the column, and you want to get 0 because that represents your remainder. Now we started with the cubic function and we're dividing out x plus 1, so we will be left with a quadratic. That means it's going to be 3x squared, +4x, -1, just using the numbers from our division. And then from here, 3x squared plus 4x minus 1, that cannot be factored, so I am going to have to do quadratic formula on it. So the first bracket gives me an x-intercept of -1. And then the second one, I'm going to do quadratic formula. So -4 plus or minus 4 squared minus 4 times 3 times -1 all over 2 times 3. So that's going to be -4 plus or minus, it's going to be all over 6. And it'll be the square root of 28. Now I can simplify the radical if I wanted to, but because I just want to graph this, I am going to turn these into decimals. So when I evaluate these in my calculator, I get 0.22, 0, and -1.55, 0. So some good information here. We have a y-intercept, x-intercepts, 3 of them, all with advanced functions knowledge. Okay. So I'm just going to start my sketch and start plotting some things. It's going to be very rough, but that's okay. Now, normally I wouldn't start on my sketch maybe right away because I don't know what scale to use. I don't know where my max and mins will be. So I'm just gonna plot my x-intercepts because that scale I am confident with. So we have an x-intercept at -1, at 0.22, and at -1.55. There we are. And I'll just do a little label. -1.22. Okay, I'm not going to plot the y-intercept just yet, just because I want to wait and see what scale I need once I actually find those max and mins. All right, next let's go to our first derivative and the first derivative test. So f prime of x is going to be 9x squared plus 14x plus 3. And then I'm going to set this equal to 0. There's no GCF. And we could try to factor with crisscross or decomposition, whatever you use. But unfortunately, this will not factor. So we're going to have another quadratic formula. X equals -14 plus or minus the square root. And here I'm just going to punch this into my calculator just to save us a little bit of space and time. I'm going to do 14 squared minus 4 times 9 times 3, so just b squared minus 4ac, and we get 88 all over 2 times the a value, so 2 times 9 is 18. And we get approximately -0.26 and -1.30, so 1.3 for our critical points. Now I am going to do a sign analysis to see if they're max or mins, and then I'll also find the actual coordinates themselves to plot. Now when we're doing our first derivative test, we want to think about our domain. We're going from -infinity to infinity, and we want to use the critical points. So -infinity to -1.3, -1.3 to -0.26, and -0.26 to infinity. And we're subbing in to our first derivative because we want to see if we have positive or negative tangent lines, because that will tell us if we're increasing or decreasing. So if I sub in a value, let's say I'm going to test -2 into the derivative equation here, I do end up with a positive number. If I sub in, let's say -1, I will end up with a negative number. And feel free to pause the video and do the sign analysis for yourself. If I sub in +1 for my last interval, I do end up with a positive number. So that means our function will begin increasing, which is kind of what we were expecting because we're starting from quadrant 3 and heading upwards. Then we're going to decrease, and then we're going to increase again, which means that we have a maximum at -1.3, which I'll sub into the original function to get the full coordinate in a minute, and we have a minimum at -0.26, and I'll sub that in as well to get the coordinate itself. So when I sub in x equals -1.3 into the function, not into the derivative, I get 0.34. When I sub in -0.26 into that cubic, I get -1.36. So these are supposed to be the local max and mins. I don't need a giant scale, so I am going to plot these local max and mins, and I'll also plot that y-intercept while I'm at it. So my scale really doesn't have to go very far. So I'll just put a few tick marks here. 1, 2, 3, 4, 1, 2, 3, 4. Okay, the y-intercept was 0, -1. Here it is. The first critical point, so that local maximum, was at -1.3, comma 0.34. So something like that. And then the local minimum was at -0.26, comma -1.36. So maybe something like that. And I'll just label the points. negative 0.26, comma, negative 1.36. All right, so we already have an idea of it's probably gonna do this, but my second derivative will just give me a point of inflection, an extra piece of accuracy just to finish it off. So let's go to that second derivative. So I'm going to look at my first derivative and take its derivative, which will be 18x plus 14. This will be faster to solve. I'm just going to factor out a 2. Not necessary, but now I can see x is equal to negative 7 over 9. Okay, and now I'll do my second derivative test to see the concavity. And again, I'm going to use my domain, so I'm going from negative infinity to infinity, and I'm going to use this point of inflection. And actually, let's see what that is as a decimal, so negative 0.78 to infinity. Okay, let's test a value. If I pick a value less than, so if I pick, let's say, negative 1 and I sub it in, I will get negative 4, so negative. If I sub in positive 1 or 0, I'll get 14, so that's positive, which means we're concave down for the first portion of our function, and then we're concave up the rest of the way. And let's just get that coordinate. F at negative 7 over 9 equals approximately negative 0.51. Okay, so let's plot our final point and connect the dots. So negative 0.77, okay, and negative 0.5, maybe something like this. So to the left of that point, we're going to be concave down like a parabola opening downwards, and then the rest of the way we're going to be concave up like a parabola opening up. And I'll just label this point here. And there we are. So we did add some accuracy compared to advanced functions, that we now have accurate max and mins, like local max and mins, and we also have this inflection point. And you might say for a polynomial function, it didn't add that much to it. We already knew the shape back in advanced functions. But now we do have the accuracy of those max and mins that would help with those optimization questions. And sometimes you might not have x-intercepts on your graph, or you have x-intercepts that you can't solve for because you can't factor. So the only guide you would have are these critical points and points of inflection, so that would help with the graphing. All right, let's get into a rational example. Now we're just going to do one, so I'm just going to scroll down and write the new equation. But you do have to think back to advanced functions because there were quite a few different scenarios we looked at. Particularly, do we have an oblique asymptote? Do we have horizontal asymptotes? And the example that I have selected for us has an oblique asymptote. I tried to make it as fancy as possible. So first, we're just going to do our advanced functions knowledge, which is I need to factor this, I need to find intercepts, I need to find asymptotes, and potential crossover points. So I'm going to factor. I'm going to take out a negative x, so that we're left with 4x squared minus 1. That means I have a difference of squares on top. I also have one on the bottom, so I'll factor that. And now let's finish with the top. 2x plus 1 and 2x minus 1 on the bottom, x plus 1, x minus 1. Nothing canceled out, which means we don't have any holes, but we do have vertical asymptotes at x equals negative 1 and x equals positive 1. And I'm going to do the oblique asymptote just in a second because that's going to take a little bit longer. I'm going to get my x-intercepts. The x-intercepts come from the numerator. So we have 0, 0. We have negative 0.5, 0. And we have positive 0.5, 0. and our y-intercept setting x equal to 0, 0, 0, which we should have expected since that was one of our x-intercepts. Now, for the oblique asymptote, I am going to do the division. So numerator divided by denominator. Now, I'm going to put my numerator under the division sign. And if I am missing any terms, I will add a 0 in there. So I'm missing the x squared term. So I'm going to write plus 0x squared. Then plus x, then plus 0. And I'm going to do the same thing for the divisor. All right. And now I ask myself, what times x squared gives me negative 4x cubed? Well, that's negative 4x. So negative 4x cubed, and then negative 4x times 0 is 0. Negative 4x times negative 1 is positive 4x. And now we subtract. The x cubes cancel out, the x squares are gone, and then x minus 4x is negative 3x. Bring the 0 down. And then actually from here, I can't do anything else because I was doing a cubic divided by a quadratic. So anything else that I add, like if I do a constant, the constant times x squared is x squared. And I already canceled out my x squared. So what we're left with is actually our remainder, and our oblique asymptote is just y equals negative 4x. Now, whenever we have oblique asymptotes or horizontal asymptotes, we might have a crossover point. So I am going to solve for that. And we just set our oblique or horizontal asymptote equal to our function. So negative 4x is going to equal, and I'm going to go into the original one. Nothing had crossed out, so I like this one where everything is expanded better. And now I'm just going to cross multiply here. And negative 4x times x squared, negative 4x times negative 1, and that's equal to the numerator times 1. And now the negative 4x cubes cancel out, and then when I bring the x over to the other side, I'll have 3x's equals 0, which means x equals 0. And if I set x equal to 0 in that oblique asymptote, it's the origin, so our y-intercept is a crossover point. All right, there's all of our advanced function stuff. And I think I will, actually, I'm not going to start my graph just yet. I'm just going to highlight the information that we will need. We'll need our asymptotes. We'll need our x-intercept, y-intercept, oblique asymptote, and I'm not going to circle the crossover point because we already had it anyway. So I'm going to go to my derivatives because I don't know what my scale should be, so I can't even really start plotting my oblique asymptote. All right. All right, let's get into that first derivative. So g prime of x is going to be the derivative of the numerator, so negative 12x squared plus 1 times the denominator minus derivative of the denominator, which is 2x, times the numerator all over the denominator squared. Now I'm going to expand and simplify here because there's no GCF that I notice that I could cancel out, make my life easier. So negative 12 x to the power of 4 plus 12x squared plus x squared minus 1. And then for the other bracket, plus 8x4 minus 2x squared. And then all over that denominator, and I forgot to put to the power of 2. And now I'll collect my like terms. So we'll have negative 4x to the power of 4 plus 11x squared minus 1 all over x squared minus 1 all squared. And now I'm going to set this equal to 0. Now, when I set this equal to 0 and I cross multiply, I am just going to be looking at my numerator. Now, although it is to the power of 4, I'm not going to do synthetic division because this does have a nice trinomial format of x to the power of 4, then x squared, then constant. Unfortunately, this isn't factorable, but I can do quadratic formula. And when I do quadratic formula, actually, let me write this in a different way. Imagine it was x squared all squared plus 11 times x squared minus 1. Normally, we would have x squared, x constant, but now we have x squared all squared, then the x squared, then the constant. So when I'm doing my quadratic formula, I'm not going to be solving for x, I'm going to be solving for x squared. Okay. Just like if I were to do crisscross, I wouldn't do x times x, I'd have x squared and x squared to get me to that x4. And now, negative 11 plus or minus the square root of 11 squared minus 4 times negative 4 times negative 1. Just going to punch that into my calculator, save a little space, all over 2 times negative 4, so negative 8. Okay, and this is going to give us the values approximately 0.09 and 2.66, but that's what x squared is equal to. Now I have to square root these numbers. And when I square root, I'm going to have plus or minus the square root of each of them. So I'll have plus or minus 0.31 and plus or minus 1.63. Those are my critical points. And I can go ahead and do my first derivative test. Now, when I do my first derivative test, I'm going to use the critical points. I'm going to use the vertical asymptotes as well. So there's going to be a lot going on here. But I'm just gonna, because I have some nice little space here, I'm going to find each value. So this is gonna be a tedious one. I tried to put a intense rational function to hit every skill. So I'm just gonna sub these x values in to the original function to get actual coordinates. So when x is negative 1.63, it's 9.47. Don't know if it's a max or a min or anything like that, but I still have a coordinate. Gives me an idea for my scale. And now for x equals negative 0.31, I get 0.21. When x is 0.31, I get negative 0.21. And when x is 1.63, I get negative 9.47. And now it's time for our first derivative test to see if these are local max or mins and to get an idea for our intervals of increase and decrease. So it's going to be a big chart. I'm going to start from negative infinity. And remember, I also have to add my vertical asymptotes, which are at plus or minus 1. So we're going to go from negative infinity to negative 1.63. Negative 1.63 to negative 1, negative 1 to negative 0.31, negative 0.31 to positive 0.31, 0.31 to 1, 1 to 1.63, and 1.63 to infinity. And we're going to punch this into our first derivative. And I'm just going to look back to the first derivative. I don't want to punch things all in one go. I think it would be easier to punch into the numerator, then the denominator, and then take the overall sign. And the reason I'm doing this is my denominator is positive always because it's to the power of 2, so I don't even have to test that. I'm just going to test the numerator. So if I try, let's say, negative 2, and please feel free to pause the video here because I'm just going to do the sign analysis quickly. I've already done it, so I'm going to put the signs pretty quickly. So if you want to pause to do it for yourself, please do. So if I pick, let's say, negative 2, I will get a negative value. If I pick, let's say, negative 1.1, I'll get a positive. For the next interval, maybe negative 0.5, I'll also get a positive. If I pick 0, I'll get negative. If I pick, let's say, 0.5, I'll get a positive. if I pick 1.5 positive, if I pick 2 negative. So my overall sign is negative, so we're going to start off decreasing, then we're going to increase, then after the asymptote, because this is the vertical asymptote, we're going to continue increasing, then we're going to decrease, then we're going to increase again, then we hit a vertical asymptote, and then we continue increasing and decrease the rest of the way. So now let's label our max and mins. At negative 1.63, we have a minimum because we go from decrease to increase. Then at 0.31, we have a maximum. Then at 0.31, we have another minimum. And then finally at 1.63, we have a maximum. We can see by how things are increasing and decreasing to see if we have that max or min. Wonderful. Now at this point, maybe I should start putting some things on a sketch before I do my second derivative, just because there's a lot of information here, so a lot to get on a graph. But I do see now that for my y-axis, I should definitely go to beyond maybe 10 and negative 10. Okay, I'm going to start my graph to the side here. So for my x's, we're not getting too far with the x's. So I think for the x's, I'm just going to go to 5. 2, 3, 4, 5. 2, 3, 4, 5. For the y's, I'm going to go to 10, and I'm just going to label 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there we go. And now I'm going to start plotting. I have a vertical asymptote at negative 1. I have an x-intercept and y-intercept at 0. Actually, let's switch colors. I have another one at negative 1/2 and at positive 1/2. And I have an oblique asymptote at y equals negative 4x. So it's going to start at the origin and think about slope, like rise over run. I'm going to go down 4, run 1. Down 4, run 1. And then I'll just connect those dots with a dotted line, and I'll do the same thing in the other direction. Up 4, right 1, up 4, right 1 again, continue. If I had a nice grid, then I could have just connected my dots with a ruler. All right, here is what we have, and now I'll put those max and mins. So negative 1.63, comma 9.47. So maybe something like that. That's going to be a minimum. So we're probably heading upwards around those asymptotes. Then at negative 0.3, we're at 0.2. So very close. But we're not crossing over the oblique asymptote. So maybe something like that. And then 0.31 comma 0.2, so maybe something like that. So maybe it's doing kind of a squiggle there. And there's that crossover at the x-intercept. And then 1.63 comma negative 9.47, so something like that. Actually, I should probably extend the asymptotes. All right, so I do have a little bit of an idea. I think we're gonna have something like this, something like this here, following those asymptotes. And here, maybe we have something like that. We cross over and then we follow the vertical asymptotes. So good shape here, but I am gonna do that second derivative test to see if I can get a little bit more information. All right. Okay, so let me just write that derivative here so I don't have to go up and down. Okay, let's do that second derivative now. So derivative of the numerator times the denominator minus derivative of the denominator. So we have a chain rule here. So there's the outside function, there's the inside function. Now the original numerator all over, denominator, now it's to the power of 4. So now I do see a common denominator on top. I see x squared minus 1. There's 2 of them here, 1 of them here. So I'll be left with the negative 16x cubed plus, oh, actually, I can factor out more than that. Because this has a GCF of x and I have an x here, I could take that out as well. So actually I'll take out an x. And maybe even a 2x. All right. When I factor out the 2x from that first bracket, we'll have negative 8x squared plus 11. Then when I take out one of the x squared minus 1 brackets, I still have another one left. I factor out the 2, I factor out the bracket, I factor out the x, so I'm just left with the 2, and then this bracket. And now we can cancel out one of these brackets. So now I'm just going to clean up on top. So there's the 2x. Now I'm going to distribute negative 8x cubed plus 8x squared plus 11x squared minus 11, and then plus 8x to the 4. Oh, actually, sorry. There should have been a 4 here. X squared with x squared. And then minus 22x squared plus 2. And now to collect like terms, these cancel. So we have 8 plus 11, we have 19x squared, and then we're subtracting 22x squared, so we have negative 3x squared, and then negative 11 plus 2 is negative 9. Now I'm going to set this derivative equal to 0. So that means we have 0 equals 2x, negative 3x squared minus 9, 2x equals 0. So x equals 0 can be a point of inflection. Over here, if I bring that negative 9 over, it becomes positive 9. And then I'm going to try to square root a negative. So this has no solution. So our only point of inflection, potential one, is going to be 0, 0, that y-intercept. And when I do my sign analysis, it's going to be with the vertical asymptotes and 0. So this one's not going to be as crazy as the first derivative. So negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. And these are the vertical asymptotes here. And I'm going to test into 2x, negative 3x squared minus 9, x squared minus 1 cubed, and then overall. So if I test negative 2, this is negative, negative 0.5, this is negative, 0.5, this is positive, and positive. For negative 3x squared minus 9, if I test negative 2, it's going to be negative. If I test negative 0.5, this is also going to be negative. If I test 0.5, it's actually always going to be negative. If you think about the shape of this parabola, it's opening down, and the optimal value is negative 9, so it's always going to be negative. And then for x squared minus 1 all cubed, if I test negative 2, it'll be positive. If I test negative 0.5, negative. If I test 0.5, negative. And if I test 2, positive. So that means to the left of that first vertical asymptote, we're going to be concave up. Then we're going to be concave down until that point of inflection. And then we're going to be concave up again. And then concave down again. So I actually didn't get anything new in terms of coordinates, but I can talk about concavity now. So let's zoom out and look at our sketch. So I need to be concave up to the left of the asymptote, which is kind of what I was predicting. I'm going to follow the asymptotes and go to that local minimum. Then we need to be concave down to the left of 0. So kind of like a parabola opening down and following the asymptote. Then we want to be concave up and then following the asymptote. And then concave down here between the asymptotes. And there we have it. So we definitely in advanced functions wouldn't have been able to figure out these points here. And we wouldn't have known that here we'd have this little squiggle happening as if it were a cubic function. So for the rational function, these derivative tests really did help.